and remote sensing systems. He received his bachelor's degree in electrical engineering from the University of Texas at Arlington, and his master's in electrical engineering too from the University of Illinois. He's a Quality System Engineer Fellow and had become the head of the Instrument Product Development Group at Ball Aerospace in 1997. This group is responsible for the design, build, and test of instruments for all of Ball Aerospace space programs. The group maintains a design and product heritage and provides overall technical activities on instrument programs, so that means it's heavily involved in many of the things that Ball Aerospace produces. His duties in the group include overall direction and management of core instrument technologies and programs, engineering team development and management, and principal lead on instrument new business activities. So
thank you.
Welcome.
Great.
To the program.
Thank you. Is this working?
Yes.
Okay, good. Well, good afternoon. It's great to be here. It's a lot of fun to talk about some of the things I do to people who are interested in these fields or interested in going in these fields. So today I want to talk about something that's pretty current that I've been working on now since about 1999. And that's how long it took for us to win a program. And then actually we won it twice. But that's another story. And then actually start the program. That's what you get into with government contracting sometimes. So this is for the Landsat program. I'll talk a little bit about the Landsat program in a minute. But this particular instrument here has been a culmination of a heritage of a long time. But let me get into a little bit more as we move through the talk. I have been involved, though, in a number of remote sensing systems over the years. My first one was in the 1980s with the shuttle imaging radar. Some of you may have heard of that for radar images of the Earth. Then I built, with the team, of course, the QuickBird series of instruments for digital globe, WorldView 1, 2, and now we're working on WorldView 3, as well as this operational land imager, to name a few of the things. We have a launch coming up this month where the ozone mapping and profiling suite will be launched on the MPP satellite, was one of the instruments I worked on. So when we go to the next chart here. So I want to first give you an overview of what Landsat is in case you're not familiar with it. Then I'll talk about the Landsat Data Continuity Mission, LDCM, which is the instrument which is the program that we're building this instrument for, which is called the Operational Land Imager. Now I'll give you an overview of that and some of the performance. Okay. Next slide. So Landsat, if you're not familiar, is a mission basically to study about how the Earth is changing and what are the consequences for us here on Earth. So the idea is to monitor the Earth over a period of time, look at things such as human impact as well as the other impacts of the evolving nature of the Earth. Landsat uses this data within its Earth Science Division, one of the various parts of NASA, for land use change, terrestrial ecosystems, biodiversity, cryospheric sciences, and earth science applications. So that's what Landsat is all about in a nutshell. Next chart. This is a history of the Landsat program. Basically, the first satellite was launched in '72. That's its period, called Landsat 1. And since that time, there's been continuous coverage of monitoring the Earth through these programs. So it's important that all these satellites and the imageries that come from these satellites are very consistent. The data is consistent, spectral bands, calibration of the instrument is consistent, and so on. The initial instrument built was called, get out of your way there, a thematic mapper. Go back one, sorry, right? A thematic mapper. Then the next instrument was enhanced thematic mapper, enhanced thematic mapper plus, and now this new generation instrument called the Operational Land Imager, OLI, is what we're building now have built for the Landsat Data Continuity Mission. Okay. So what I want to show you is just an example here of some of the data that comes from Landsat. This is Las Vegas in 1987. So there's a series of charts here, and maybe you can cycle through them and see how Las Vegas itself has changed. So once you cycle, okay, so there's 1999, 2008. So maybe you can go back. You can see the change of how Las Vegas has grown. Notice the drought here that happened here in 1990 or 2008. You can see that. So I'm not going to try to go through the science here, but I just wanted you to get an idea of one of the things that Landsat data is used for. So now let's go to the next one. So this is an example that I like. This is the Yellowstone. You remember Yellowstone National Park basically caught on fire in 1988. And this is the Landsat data from 1987 here before the fire. There are 3 bands being monitored here, the green band, near-infrared band, and the shortwave IR band 1. Notice there's the Firehole River, the Prismatic Spring, Old Faithful is here, and this is the park boundary. And if you notice, that's a pretty well delineated boundary. And the reason it's so delineated is that grazing, open field grazing, was allowed on non-park lands, but not on the park itself. So the animals graze right up to the park boundary, and you can see the differences in the structure of the earth that you can see from space. The dark colors here are the old growth forests in there. Lighter ones are newer growth and fields. Around, if you look at around some of the springs here, that pale yellow is a high mineral content area. The lakes, for example, are dark blue. So what I've got here is a movie. Maybe you can cue up the movie that is a mosaic, well actually not a mosaic, but a movie of the images taken from before the fire, through the period of the fire, and then the recovery up to about 2008. So notice that change there as you're going through. The date's right over here. You can follow the date as we go along. All right. Maybe we can cycle through this a little bit as we go through. But you notice a slow recovery, over a decade here, what it takes for the land to come back. There's a fire, there's it spreads, there's it starts to come back, and the growth begins to come back. But as you'll notice as we go through this, cloud cover you see go through there, as we go through this, after a decade, it still not has repaired itself from the fires that were burning in Yellowstone for a period of time. One of the reasons this is so interesting for me is I was there in 1988 with my family at Yellowstone when the fire began. And we got to see the smoke coming across the park as we were exiting the park that year. But this is the idea of what a long-term monitoring of the Earth's surface will tell you, what you can find, how you can use it for Earth resource management. So maybe we can go on now back to the, okay, great. So let's go into the next chart. Now I'll talk about the Landsat Data Continuity Mission next. So here is the mission at the top level, mission operation, mission ops it's sometimes called, for Landsat, LDCM. We're flying now a legacy orbit, same orbit that all the other Landsat missions have flown in, which is nominally 705 kilometer orbit. Okay, it's a sun synchronous orbit, meaning that as you go around the Earth, the sun is in the same position relative to the satellite. The Earth is spinning around right underneath it, but the orbit is the same track. So when you cross over a period of land mass, for example, at the equator here, this is called a descending node orbit. So the satellite comes across here in the orbit path. It crosses the equator at about 10 a.m. local time. So the sun is always in the same place, which is what you want for monitoring change. You want to have the same illumination, same solar position for all these images. They follow a path that's well-defined, 16-day repeat. It's what's called the World Reference System 2. And it is a whole set of scenes, basically, that are used to build up the images around the Earth. So you can go back to 1972 and say, give me this particular WRS2 scene, and you can pull it up. And it'll be that same position on the Earth. that same scene position throughout. So we're collecting data from the visible all the way through actually the thermal infrared, TIR, that's what that means. So you have near infrared, shortwave infrared, and thermal infrared, which is about 8 to 10 micron, 8 to 12 micron band is a thermal infrared. The instrument that we just built at Ball just encompasses the visible, near IR, and shortwave IR part of the spectrum. There's a separate instrument for the thermal infrared. So we're providing global land coverage all parts of the year, all parts of the season, collecting 400 of these scenes per day was one of the requirements. And we also have to maintain a rigorous calibration and, of course, archiving all the data products, which is done by USGS through its Sioux Falls Center. Next chart. This is an overlay of the bands. So what you're looking here is basically the spectral transmittance through the atmosphere from 400 nanometers up to almost 2.5 microns. And you can see there's portions in the spectrum that the atmosphere completely filters out, any light from coming in. One of those is right here at 1375 nanometers. That's a cirrus band, the cirrus cloud band right there. So these bands were chosen to look at specific things on the Earth, specific things in the atmosphere. The legacy bands here, this is Landsat 7 bands. They had a blue, green, red, near-infrared, panchromatic band, shortwave IR1 band, and shortwave IR2 band. Landsat Data Continuity Mission actually added 2 more bands, one up here at the coastal aerosol and one for monitoring cirrus clouds. Cirrus band is kind of interesting. You can look at it from space and you won't see anything except for tops of mountains sometimes. And that's because the atmosphere blocks most of that light from coming through. And so that's a good band for monitoring the level of cirrus clouds in your data and using that to correct data. So let's go on. Obviously, we have to have a standard such that the light we measure, the radiometric accuracy that we measure is consistent. So you can monitor change. If you don't have good calibration, then you can't monitor change. And so this is a chart showing the total, this is top of the atmosphere TOA radiance. In other words, it's what you would see basically from the solar irradiance at the top of the atmosphere without any atmospheric effects. And that's where the calibrations are done. And this is from Landsat 1, 1972, throughout the period now, up through Landsat, Landsat 5, I guess, is on this chart right here. And basically, this is a plot of, I believe, the band 4, which is a near-infrared band. So you can see the overall requirements of the mission is a 1 sigma uncertainty of about 5%. We were able to achieve about 4% through that. All right, next. So let me talk to you about the instrument we built. Next chart. So this shows the legacy instrument. This one is actually the what's called the Enhanced Thematic Mapper Plus, ETM Plus. And the way it worked, it's called a whisk broom scanner. And what that means is as the satellite's flying over the Earth, it has a scan mirror in it that basically paints the scene, scanning back and forth as you go across the Earth, and that's how it builds up the images. In contrast to OLI, which is the next generation, change in how these things are done is called a push broom scattering. So you have a row of detectors through your optics over the full, what's called swath of the instrument. That's the area that you're actually sampling within your field of view. And satellite motion actually then scans it along the ground. So it's called a push broom, just like a push broom versus a whisk broom you would use on your floor in the kitchen, right? So what that gives you is a lot more time to integrate signal as you're going across. Because instead of in one line time having to move across and integrate all of your pixels across the full swath, which for a Landsat it's a 185 kilometer scene that you're painting out at a 30-meter sampling. Okay, so we're sampling, each pixel in this picture is 30 meters in the multispectral bands that's sampled across 185 kilometers is what this scene is. All right, so this instrument then now gives you a much better signal noise ratio because we have a lot longer time to integrate. So that's one of the things. This is what's called an unobscured telescope, if you're familiar with the term. A lot of the centered system have a secondary mirror in the way, in the path, and less light obviously can get in, and also then causes some contrast issues. Where an unobscured system, the light is not blocked. I'll talk to you a little bit about that, and gives you much better contrast in your image, which is important for radiometry, that you're looking at a piece on the ground. You need to know that the light coming from that piece is what you're collecting and not light from someplace else. So that's very important. We also have a dynamic range of 12 bits versus 8 bits for the older data, so we'll have a lot more resolution within the radiometric data that we have. Let's go to the next chart. These are the bands, and if you're interested, I told you they range from 443 nanometers for the coastal aerosol, typical blue, green, red, and near-infrared bands, 3 shortwave IR bands, 2 call it SWIR 1 and SWIR 2, and then our Cirrus band, and then a panchromatic band. The sampling is 30 meters GSD, 30 meters on the ground, except for the pan, which is twice that in each dimension, so 15 meter sampling. All right, these were the required signal noise ratios right there. Then it just shows you a plot here of the top of the atmosphere, solar units, the various bands within that. This is a band here that's a typical desert scene, a typical scene that we would have from vegetation coming off the Earth. All right, let's go to the next one. So this is the instrument that we designed and built at Ball to meet the requirements of this mission. So this is a little cartoon form, and I'll walk you through what this is. We have a system here. Let's start up here. This is the Earth viewing port. So the light from the Earth enters the telescope at this point, goes through a 4-mirror telescope system, and is imaged onto a focal plane here. Focal plane then contains our detectors for, basically transforming photons into electrons, and then we digitize that and send that down. There's also a port here that's a calibration port. We call it a solar port, solar viewing port, that we actually use to look at the sun. We use the sun as a primary calibrator for this system. All right, and we have a mechanism here that actually puts that's open when we're viewing the Earth, of course, but puts in a spectral-on reflector system. It's a Lambertian reflector. Lambertian meaning that it's like your piece of paper. You look at almost any angle, and the amount of light looks the same. Okay, that's what a Lambertian reflector is. Okay, and so that actually then lights up the inside of the telescope, and then we run calibration images through that based upon the sun as our standard. All right, I'll tell you about how we do that a little bit in a minute. So the light is imaged here onto the focal plane. We have various modules that build up our full size of our focal plane over the 9 spectral bands that we have. The data is these detectors. This is a new technology that was developed for this program, in that we have a silicon PIN detector for the visible near infrared, and then we have mercad telluride detectors for the shortwave IR. And both of those detectors and those rows of detectors are attached to a CMOS integrated circuit. It's called a readout integrated circuit. And basically they do all the sampling and the muxing of those signals and then bring those out in a video stream that we then take through our analog circuitry, convert that. Actually, we convert to 14 bits of data. We have 14-bit analog digital converters. We truncate 2 of those bits before it's actually sent to the ground. So all the control for that is done in this box. And we also have what we call the instrument support electronics that basically is the brains of the system that communicates with the spacecraft, that does all of our basically command and control of our instrument, controls it thermally, takes commands from the spacecraft, moves mechanisms in and out, so on and so forth. Additionally, we have a shutter up here at the aperture that we can close off, because when you're calibrating, you want to see what is a good dark background, right? And so we have a shutter that closes off. We can take dark images. Then we can take an image of the reflector here, the solar calibrator, and we can do that at various integration times. So we actually can develop a linearity curve for our system on orbit through the sun. So that's what it looks like. This is a top view of a drawing that shows the fields of view for both of these ports, the solar port as well as the imaging port, and these are actually keep-out zones because you don't want to get light, say, glinting, reflecting off a piece of spacecraft into your system that will then corrupt, what you're trying to do. So let's go to the next chart. So this is a more detailed picture of the design, all right? Again, here is the entrance port here, entrance aperture. The light goes into the telescope here, goes through the 4 mirrors down to a focal plane down in this area right here. Focal plane electronics have to be close, so they're actually built and designed to be very close to where the focal plane array is. The imaging support electronics are behind here. This is a radiator for cooling those electronics. On this side over here we have some very large radiators. This system is passively controlled as opposed to having a cryo cooler. So we get our cold sink from these big radiators. These run at about 185 Kelvin. When they're pointed away without any earth shine on them, looking at deep space, they get that cold. So then we have heat pipes, which are high conductance thermal pass to cool off our focal plane. Focal plane needs to run at about 207 Kelvin. So it's a cold focal plane. That allows the detectors then to image to the quality that we need. This solar port here is for viewing the sun. So when we're ready to do a calibration, the spacecraft actually maneuvers the instrument around. So this solar port right here views the sun. Obviously, prior to that time, we have engaged our mechanism to block out the entrance aperture and put in this solar diffuser in that path. Sun illuminates the solar diffuser. Light then goes into the telescope for a very well-known radiance calibration against the sun. So that's basically how the system works. It's mounted to this base plate, which is a composite material, graphite composite material, very thermally stable, because we have to keep the pointing of this thing very accurate so we know what we're imaging on the ground. All right? So let's move on to the next one. Another view of the system, I want just to walk through the calibrator with you a bit. Solar viewing port is here. All right? These are the solar diffusers embedded into this wheel. There are actually 2 of them. There's, besides the open port here, so when we're doing Earth viewing, there's one of these here that we call a working diffuser, and we do a calibration every 16 days. So it'll be moved into place, images the sun, and then moved out of place. The shutter here, we actually do that before and after every image. So it's used twice per orbit. So I use a lot of times we take a dark calibration to know where our background is. The second diffuser in here is called the pristine diffuser, and it's used once every 6 months, because what these diffusers do over a period of time, they degrade. The UV and the light will actually cause these things to degrade. If there are any contamination on these at all, then that UV light actually will then cause the contamination to blacken, and so we get different reflectance properties off of this diffuser. So it's used as a backup for checking how much degradation that we have in that system. In addition, we have calibration lamps that are mounted up here by our entrance aperture. These are tungsten lamps that have internal monitoring for radiometry, give a very stable illumination of the system all the way through to the focal plane. They're also used for calibration as well. All right, next chart here. So this is a view of some of the hardware during the integration phase. This is actually the completed instrument itself, all right, less the thermal control and the base plate it sits on. So most of our performance testing was actually done in this configuration. Notice the electronics box here. This is the instrument support electronics that controls the full instrument. These are the 2 solar diffusers I mentioned on this wheel. This is the entrance aperture. It's actually covered up now for contamination reasons. We remove these shower caps right before flight. After we're integrated to the launch vehicle, they're the last thing that are removed because it protects the instrument from contamination. This is the telescope itself in a graphite composite structure that's very thermally stable, and various holding fixtures here to use when we test the instrument in different configurations. Thermal control system is here. There are actually two radiators, one for the focal plane array, which is the large one, and associated heat pipes that come down here that have to be thermally isolated from the rest of the system. And then a smaller one here that we actually use to control the electronics. So part of the whole stability of the system is not just those detectors, but also the electronics that read those. So we control those electronics at the base plate of that box to 1 degree Kelvin. So it goes plus or minus a half degree over the life of the mission. So all the A to D converters and all of that electronics associated with sampling that system are very stable because it contributes to the overall accuracy of the system. All right, let's go to the next one. So this is actually the completed instrument, and I start it because the only thing that's not on here are the thermal blankets. So we have multi-layer insulation thermal blankets that actually cover almost everything up. So if I were to show you a picture of that, you wouldn't see very much. The only thing that is not covered up are these radiators here, and of course the entrance aperture. But everything is covered up, and these blankets are actually white. They're called a Tedlar material, very efficient thermal blankets. Thermal engineering was a huge part of designing and building this instrument because of the type of temperatures we needed to maintain and the stability of those temperatures. The focal plane temperature variation is 50 millikelvin over the life of the instrument, so it does not change, and it needs to be that stable in order to get our radiometric performance of the system. So again, there's the entrance aperture. This is that big calibration wheel and solar calibrator that moves those solar diffusers, spectral-on diffusers in and out of the field of view of the system. Of course, there's a solar port over there. Gives you an idea of the size of this instrument. It weighs about 450 kilograms. That's how much it weighs. All right. And you can see from the scale how big it is. Next chart. So we had to test this instrument and calibrate it to a level that most instruments aren't calibrated. So this is one of the premier calibration campaigns in the world for any system. Landsat instruments are known for that. 5% absolute radiometric accuracy on the calibration, traceable to national standards from NIST, is very difficult to achieve. And these are some of the things that we did to calibrate it as well as to prove out its performance. So let me walk you through some of these things, and we'll talk about them a little bit. So we're going pretty good for time here. This blue here is actually a vacuum chamber. So we have a large vacuum chamber that the whole instrument fits inside. We have a number of these at Ball, and we use those for testing in flight-like conditions, in vacuum, at temperature that you would see if you were actually flying an instrument. And so all of our testing is done within these thermovac chambers. So then we have to, the challenge is to provide a test platform so that you can actually get the light in and get the data out while the instrument sees flight-like conditions. So this right here is an integrating sphere. Now, an integrating sphere is basically a large sphere that's got a high reflective material in a Lambertian sense. Inside the sphere, it's illuminated with lamps so that it presents a uniform aperture, very stable light to the instrument, and they're used for calibration on the ground. The integrating spheres, this one was actually called the Death Star sphere because it kind of looked like the Death Star, and you'll see that in a minute. So those one of the tests we did for calibration is to use this. Is actually butted up against a chamber window, an optical window in the chamber, so that the solar or the Earth viewing aperture is aimed at this integrating sphere, and then we collect a lot of data in numerous times, numerous different conditions, temperature and so on, in order to calibrate the instrument. The second thing that we had in order to maintain what's called a transfer to orbit calibration, since on orbit we'll be calibrating against the sun, our approach was to calibrate against the sun on the Earth. So we actually built what's called a heliostat to enable us to do that. And what the heliostat does is bring in sunlight from the roof of our building down into this optical chamber. So now this is that big big vacuum chamber, sorry. This is a big vacuum chamber. We have an optical port right here. That port is actually looking right in at this solar calibrator port on the instrument that I described earlier. This is a relay mirror here. So now the sun is coming down, being reflected inside that chamber so we can illuminate that solar diffuser calibration. Notice this guy's hand right here in front of it. I'll show you something on that in a minute, so just keep that in mind. We also had to calibrate the instrument and characterize it, how it responds to various wavelengths of light, called a spectral calibration or spectral measurement. So we had a very fancy piece of ground support equipment that we had to build up in order to do that accurately. And we also tested that through the optical port of this chamber. Another test we had to build to show that we had performance is a polarization test. So lights coming off the Earth, it can be polarized by the different scenes you're looking on the Earth, whether it's water or vegetation or whatever. This system has to be fairly insensitive to that polarization. In other words, we want to measure the amount of light coming off a given feature and not have it essentially perturbed by what polarization it is. So we had to prove out the system is now somewhat insensitive to polarization, various polarizations of light. So we do a test, polarization test here. We have a polarization plate that's linearly polarized that we can rotate it around and measure the response of the instrument for various polarizations and show that it meets those requirements. That was actually mounted here to this front part of the chamber optical window, illuminated by the sphere when we did those rotations to measure polarization sensitivity of the instrument. So those are some of the tests that were performed. Let's go into the next one. And so this is a suite of material, hardware, and that we needed to use to calibrate this. These things had to be traceable to NIST standards, which is difficult to do. All right, what you're seeing here is this Death Star sphere. Now you can see why we call it the Death Star. And it actually has a water-cooled jacket on it. Now this water-cooled jacket, since you have, I think it's about 300 watts here of lamps, you have to cool this thing. And interestingly enough, when you look at this data, it was so sensitive that the instrument could actually see those cooling lines in this data here. And so it gave us structure. It wasn't very much, but there was enough structure in there that we actually had to characterize the sphere and then correct for that structure in order to show that we met requirements. The smaller spheres here had various purposes. This one here was a sphere that was used actually as a transfer calibration. All right, so what we did is we shipped this sphere off to NIST in Gaithersburg, and they calibrated it to national standards. Now, along with it, we shipped some of these radiometers. These are very precise calibrated radiometers for measuring intensity of light in the various spectral bands. So we shipped those both off. It was calibrated. We measured it against our radiometer. It was shipped back to Ball, and then we did that measurement again to show it hadn't changed in the shipping process. So then by the combination of these radiometers and that sphere, we were able to transfer the calibration to this larger sphere, for example. So then through the whole air budget tree, we were able to show that in the end, we were able to meet the requirements from NASA. We were actually able to achieve about a 4% accuracy for absolute radiometric calibration. Next chart. So this is that heliostat, okay? And you can come over to Ball and see this on top of one of our buildings here in Boulder, all right? This is it up here, a diagram of it. We have one of our optic here that actually tracks the sun. And there's software associated with tracking it. We also have some sensors that tracks the sun. The requirement for this system was that any time of the year, we had to be able to produce 4 hours of a continuous solar calibration capability to certain accuracies. So obviously in the wintertime when the sun is the lowest, it was the most challenging to do that. But we were able to do that. So it tracks the sun, goes through a relay mirror down to this chamber, and there's another then fold mirror there to direct the light inside the chamber. This is what it looks like up on the roof. There's that tracking mirror right there. It reflects the sun into a relay set of optics here, then that go down through the roof of the building and then is reflected back into, remember where I see the guy holding his hand out in front of it? That was that reflecting mirror, okay, that reflects it into the chamber. This is the view looking back into this relay optics when the sun is illuminating it right here. So the sun is illuminating this heliostat that then gets then fed down. Now, while we're doing this, we have to make sure that we have a very well-known solar irradiance. So the atmosphere makes a difference. So we're tracking what some of these guys are doing. These are guys from the University of Arizona. They're actually tracking the sun, determining atmospheric, various atmospheric effects of the light coming down. I'll talk about that in just a minute. Next. So once that's reflected down, and then it goes inside the chamber. So this is the chamber window that I was showing you earlier. Now this is that solar port on the instrument. And you can see the solar baffles. And what you're looking at right there is that solar calibrator, that diffuser, solar diffuser, spectral line material. Remember the guy had his hand out in front of it? He was actually taking this photograph at the time. There's his hand, and there's the camera right there in the shadow when he took the photograph. So while we're doing this and doing the calibration, then we have radiometers mounted up on the roof which record the light that's coming in through the heliostat such that we can actually correct for atmospheric effects and then show our transfer to orbit calibration. That's what Boulder basically looks like in the spectrum when we were doing it. That's 30 degrees and at 60 degrees of the sun angle to the heliostat. Let's go next. So we used all that data, and we have to measure a number of things, okay? Signal-noise ratio is a very large one, because once you're looking at the image, you're just taking a snapshot of that image. So you don't have time to essentially average out the effects of photon noise, statistical photon noise in the image. So there is an uncertainty, right, of each photon striking that focal plane that produces noise, right? And it's called photon noise. So you can integrate over large periods of time and beat that noise down, right, square root of n. But when you're taking an image, you have a snapshot over your image, your integration time. So you want your overall signal-noise ratio of the system to be very good. The better it is, then the better knowledge you have of the radiance coming off of that scene. His comparison here, the enhanced thematic mapper, which was this whisk broom system, produced signal-noise ratios less than 50. All right. Now with this new generation whisk broom type of, or push broom type of imager, these are our actual. Whoops. Go back a couple here. One more. These are our actual signal-noise ratios in the various bands that we measured. So you can see the improvement for this kind of instrument that we're getting somewhere over 150 for essentially all of our bands. The Cirrus band is more challenged. It's narrow. It's hard to get much light into that, so it has a little lower signal-noise ratios than some of the other bands. And then the panchromatic band, of course, is a smaller sampling distance, smaller area by a factor of 4 than the other ones. So you're getting a lower signal-noise ratio for it as well. The other thing that we had to demonstrate is this thing was stable over time, stable between our calibrations. So we had to perform tests that showed the stability over 16 days, which is this chart right here. So what you're looking at here is the green band over a 16-day period of time. You set up, you calibrate it. Okay, you calibrate it, then theoretically, if you calibrate it well, you take an immediate image and it hasn't changed. You get essentially a null signal against your calibration once you applied your calibration coefficients. So the next opportunity on orbit we have to then calibrate again is 16 days. So we had to demonstrate stability over that period of time, which we did in this thermal vacuum test. That's the stability of the green band here in this particular chart versus our 1% requirement. So a very, very stable instrument. Overall, this, by the way, had to be it's a 2 sigma uncertainty requirement. So it's a little tighter than what you'd normally see in some of these things. So what we were able to achieve actually is better than about 0.5% in all except the Cirrus band, which is more of a challenge band. And its requirement is actually a 1.5% requirement. So we were able to meet its stability requirements as well. So let's go to the next one. These are the results from the spectral measurements. These are the various bands as you go through here, starting with the coastal aerosol, blue, green, red. The panchromatic band overlaps some of those, that's the black. This band here is now the near infrared band. The Cirrus band, notice is a very narrow band, the Cirrus band right in that window, that atmospheric window. Shortwave IR band 1 and shortwave IR band 2. So those are the spectral bands. We had to show that those met a very narrow spectral performance range for center wavelength as well as band edges, and also the out-of-band response of these had to be better than about 4 orders of magnitude down from the in-band response, which was also challenging to measure. The polarization factor, if you look at the ratio of your highest polarization to your lowest divided by the sum of the two, that's defined as the polarization factor. Our requirement was 5%. We were measuring across these various bands somewhere in the 1 to 2% or better range. So very good instrument. Next. In addition, we had to show that their light from out of the scene was not getting into any given pixel to a certain degree, because that's a corruption of your actual signal in a given 30-meter ground sampling distance that you're actually trying to measure. So we have some very sophisticated facilities at Ball for measuring what's called stray light, stray and scattered light, which is a facility here in which is very darkened out, very well controlled field of view, and you project a point of light, very small point of light, very narrow field of view, and then you scan it around your instrument and you look for any ghosting or any light levels, outside of where that light is. So we were able to measure our stray light in the out of field areas at better than 9 orders of magnitude down, which is very challenging to do. Additionally, we also had to measure how sharp of a response this thing had to edges on the ground. MTF, modulation transfer function, is one measure of that, which you guys may be familiar with. Our requirement was in terms of what we called an edge slope response. In other words, how sharp is an edge target actually imaged inside the instrument. And it's a ratio, typically, if you look at a very sharp edge, for example, here, in reality, that's sharp up in the projector, but on the screen it's not that sharp. It actually blurs out, okay? And so that's the type of thing you're measuring for an instrument like this, because you want to make sure that you have a very tight sampling of the piece on the ground that you're trying to measure in order to get the appropriate accurate response for monitoring these things over time. So we actually have a collimator assembly we call the HCA, horizontal collimator assembly, that is used to measure this. Actually goes inside of a vacuum chamber. So this whole piece of test equipment goes inside of a vacuum chamber, all right? Here is the OLI instrument right here. We have the targets here for measuring these response on this stage. It has to be folded around inside the chamber to off-axis parabola. That's a collimator that's actually off-axis that then collimates the light that's directed into the instrument for these measurements. And we can scan the instruments back and forth to look across the field of view and so on. This is some of the patterns that we use that's set up here to focus of that collimator that we projected into the instrument for measuring these things. Let's go to the next chart. So this is the type of data you get out of that kind of measurement, all right? And this is now translated to meters on the ground because our requirement was in meters on the ground. So we did the transformation between, microns on the focal plane to meters on the ground for these measurements. This is the actual data, all right? These are all of the multispectral bands right here. We had a slope requirement of this number. The measured value was actually a lot sharper than that. So a pixel size here, for example, would be 0 to 30. That was a 30-meter detector size, on the focal plane when it's projected out onto the Earth. So we're able then to meet the requirements of how sharp that is, how much it spread out once you get outside of a pixel, and if there was any rippling involved in that, which sometimes you would get in the older instruments. Panchromatic had to be sharper because it's 15-meter ground sampling distance, so that's right there is 1 pixel response, and you can see the data there was very good. So these are the kind of things that you'd have to measure, prove out, and we're also able then to map out every pixel in the instrument so that we know where it is when it's projected on the ground. Then we can translate that into an actual place that we're measuring, okay, for calibration. And that's an absolute geometric accuracy requirement. We were actually better than a half a pixel on that. Next chart. So just a summary, right on time it looks like, huh? So we actually shipped this instrument, it was yesterday, Sunday? Yeah, Sunday. So Sunday morning, yesterday morning, we shipped this instrument out of Ball down to Gilbert, Arizona, which is in the Phoenix area. It's being integrated on a spacecraft that's built by Orbital Sciences Corporation down there. So we have a crew of people that should have arrived by now. So the goal was to make it arrive before rush hour down there. So it should have arrived, and they're probably unloading the shipping container right now as we speak at the orbital facilities. So we'll go through a checkout procedure there and then start the integration to the spacecraft bus on the system. So the big thing here is that the OLI represents a generational change in what has been done. So the data that's from this instrument should be so much better than the previous instruments, and we'll see, you know, how the science is used once it's up there. So I'm looking forward to that. We designed the instrument before we won the program, and we focused the design on performance. So we're actually able to achieve, you know, exceed those performance requirements over the life of this build mission, and the spectral performance, the radiometric performance, the spatial performance, all these things. And then in the process, we established some fairly unique capabilities at Ball in terms of world-class calibration capability that helped Ball's position and the competitive edge for this actually go up, and now I believe that NASA considers Ball the top place in the world for these kind of calibration activities. So maybe sometimes you guys want to come see some of those things. Maybe we can arrange some time for you to come over. And most importantly, we're building these systems for our customers. So it has to meet our customer needs, and we exceeded all their needs, and I think they're very happy with us. So that's all that I have. Thank you. Yes?
The focal plane is pretty big. You didn't say how actually big it is physically.
Physically, it's the focal plane itself is that large in terms of a structure. Okay, about the center 12 inches or so is the imaging area on that. So it has 14 of these focal plane modules that are actually staggered to create the field of view. So it's about 7,000 detectors across for the multispectral bands, and then twice that for the panchromatic band.
Do aberrations vary across that large of an array?
Well, that was one of the challenges in building this instrument. It's a 15-degree field of view instrument. It's pretty wide in optical terms, right? So we had to balance a number of requirements while we ended up with a 4-mirror telescope design. That primary mirror on the telescope doesn't have any power. But it is an aspheric. It's about a 5th order aspheric, and it was required to do some of those things because not only do we had to have good wavefront performance, it's called, across the full field of view so that we could meet these spatial edge requirements, but we also had to have low distortion across the field of view. You know, in a telescope, especially a wide field, you'll get various types of distortion as you move across the field of view. So, you know, a square pixel on the focal plane is projected at something different than that on the ground. And so we had to have not only low distortion across it, but also a well-known, you know, distortion characteristic, effective focal length is called, across this field of view so that we could do mapping of all those pixels. And so we measured that down to better than the whole system actually better than a half of a detector, half of a pixel across that entire field of view, and we're able to correct down to those layers. Yeah. So we have a facility at Ball called Detector Technology Center, where we have some very precise optical measuring machines for locating each detector on the focal plane. We had a whole transfer of fiducials from the actual detectors themselves, all the way up through the whole focal plane that now gets registered to the full telescope. And so, you know, you've got your focal plane, that's a coordinate system. You have your image plane on a telescope, that's a coordinate system, and you have to mesh the two together to know overall where you are. So, yeah, it is a very large focal plane. Yes?
Do you have to, was it difficult to prove that after launch vibe this would still remain in calibration?
Difficult in the sense that you have to go through a lot. You know, we did not have any trouble achieving that. So what we do with these instruments is we have to prove that environmentally they will survive and maintain performance after launch. So that goes through the launch vibrations that you get to, which acoustics is a big part of that. Shock, acoustics, and the overall random spectra of those vibrations. So we have some big facilities at Ball. We call them shaker tables. They're actually used to sweep through that spectrum to test the system, and we tested it at levels higher than that are expected on orbit, or I'm sorry, on launch. So we'll actually shake these things at much higher levels, go back and measure them again, and look at the pre and post to prove that we don't change, you know, in the launch environment. So we do that vibration, and we do that thermal too, because it'll be a different thermal environment on orbit than on the ground. So we do thermal cycles and test of the thermal system called thermal balance to prove that the thermal system is working in the way it's supposed to work on orbit. Any other questions?
So
yeah.
How much of the optics and detectors and everything is stuff that you can buy commercially, and how much is specially manufactured for this?
Everything was specially manufactured for this program. Of course, using existing technologies to some degree. The magnitude of, for example, this what's called a focal plane subsystem, which is a detector of the focal plane, all the electronics to drive it, was about a $40 million activity, to give you an idea of the complexity of doing that. And it's not something that you can go, you know, just buy off the shelf. These things are generally designed and engineered for particular missions. For example, each one of these bands we had to design in through a process such that the amount of light they would receive, they would respond to, they wouldn't saturate, they would meet the noise requirements. And so you go through a process of looking at the whole system, flowing down those requirements all the way till you get to the detector level and say, what does this detector need to do in order to achieve these requirements? Then you spec that out and build the detectors, test against that to show that they meet your requirements, and you test all the way the phases. Excuse me, back up. Sorry. Anything else?
You mentioned you have an extra diffuser there. How much redundancy do you have in the whole system?
Oh, it's a pretty much what's called a fully block redundant system, except for some of the items. For example, the two diffusers, that whole mechanism has not only bearings in it that are high reliability and the redundant diffuser itself, but the electronics that drive the system have redundant sides. So it's block redundant for driving that mechanism. In addition to that, it has a fail-safe system on it, which is a torsion spring system with a pin puller, okay, such that if it would to lock in a certain position, you're able to pull that pin, release the spring, and it would open itself back up to the open position so the mission wouldn't fail. You wouldn't be able to calibrate it against the sun, but you'd still be able to take images.
I was thinking about the whole instrument.
The whole instrument. So the focal plane itself is not redundant in the sense, well, I'll take that back. This one actually does have redundancy in it. The focal plane itself has rows of detectors that allow you to select. In the shortwave IR bands, there's one of 3 detectors you can select across that whole row, and you can select those independently. Those were originally designed to give us high operability, which is near 100%. You don't want any bad detectors on there. But then you can also, if you lose one in orbit, you can deselect it and select another detector. Electronics behind there are redundant in a sense. We call them an N+1, that we have we have actually 2 boards. Each of those boards handle 7 of the channels. There are 14 total channels. And each one of those boards actually has 8 channels on it with electronics. So we could switch out a bad channel if one of those channels fails. It's called N+1 redundancy. Power supplies are all block redundant. We can switch either one in or out. Our instrument support electronics has fully redundant electronics on it as well. Optics aren't redundant. This thing has a focus mechanism on it. The focus mechanism has redundant electronics. Focus mechanism is intended to use only one time to take out any offsets once you get up there to launch. Shutter mechanisms is also redundant in the same way with the fail-safe on it as well. So yeah, you know, you pay, NASA pays, maybe $1 billion to launch one of these things. They want to make sure it works up there, so when it gets up there. And so that's why they design these things in, yes.
So when you're talking about polarization, you want it to be not sensitive to polarization.
Right.
Aren't you kind of throwing away some information there? Because a lot of the scenes you're looking at, I mean, the polarization would tell you something about what you're looking at.
Yeah, they would tell you. Now, for change detection, which they care about, they don't want changes in reflectance off of foliage, for example, because of polarization to show up in the data. So that's the reason they don't want it sensitive to polarization. But there are things you can learn from if you can measure polarization. This particular mission, doesn't want polarization. They want to measure light, all the light that's coming back to them, right, regardless of the polarization it's in.
Any other questions?
On the dark side of the orbit, what's the instrument do?
So the instrument is actually on all the time. A lot of these missions to conserve power is turned on and off. But this one requires such extreme stability that we need to leave it on all the time, so thermally it's always balanced. We also have requirements for taking dark images. So a certain number of those 400 scenes per day will actually be taken on the dark side of the Earth. So it works in eclipse as well as in the sun, thermally controls itself throughout the orbital cycle on all the time. We also have other targets we view. For example, one of the calibration campaigns that we have is looking at the moon. So we actually scan the moon. Moon is actually a very stable albedo source, and as long as you look at it in the same conditions. So typically a full moon, you're looking at it when it's not eclipsed by the Earth, for example, and you'll take scans of the moon and do precise radiometry on those scans. Other targets we look at are things that are ground cal called vicarious calibration, in which there are land campaigns set up to measure albedo of the area that you're looking at. There are a number of sites in the U.S. that are used for that. University of Arizona is one of the people that are probably leading the field in doing that sort of thing. They have radiometers for measuring albedo of the surface that they want to see, plus radiometers looking up at the atmospheric transmittance, and you do simultaneous flyover and collect and do a calibration that way. So I added a little bit more to my answer, but those are the things that are done, yeah.
Just to follow up on that, I was confused. I thought you were saying that the orbit was such that it could always see the sun. So.
The sun is in the same position all the time, but it does go into eclipse. So if here's the Earth, you're the sun, it's going around about like that. The Earth is turning, right? But it always remains that same position in space.
Okay.
Yeah, and then it sort of moves seasonally as you go around the sun. All right.
Let's take some.
Yeah, thank you.